did the I-squared for trend, we had to use another calculator. Hello, sir.
Yeah, I'm listening.
Hello? So what I'm asking is, does it mean that SPSS either add on or the orthodox traditional way it is, does not do trend by itself? You have to use another program, a calculator.
Okay, yeah, the question you see, if you look at, you have different statistical packages, just like this way you have different cars. And everyone will keep on improving their car based on demand from customer and taste of customer and some other things. So it's the same thing with the packages. They keep on improving. If they are not improving, they will not be having new version. So they keep on improving, doing something, because this statistic, the subject is wide, but there are something that are common. There are something that are not common. Like this trend now is not something that people commonly use. So maybe over time they will have a way of putting it inside. Like in Epinfo now, the Epinfo also does not run the trend directly, but it has a calculator. Epic, just like the way this WinPep is. If you have calculator attached to it, they calculate it for you. You still have to use them. Because after all, also, the trend also is something you can, is afterthought. After you have analyzed, you are observing some trend, and that's okay. Is it a true trend? So it's a matter of, you can actually bring out the summary and put in the calculator and calculate it. So, but it is possible after a while, they may have provision for that. And you know, if you look at the name, is statistical package for social science, and they have improved. That's just the name, but they are using it for a lot of things. So that's just it. And then when the people that develop Epinfo, they develop for epidemiology, really. But it's over time, people discover that even the SPS is more user friendly. Like Starter now, the world of academic, they are going towards Starter. But still, the graphical user interface of Starter is not as developed as that of SPS. And the SPS are business people. They try to make life easy for people. So they keep on improving on it. So maybe over some time they may be able to do that. Put it there. So any other one? Should we start? Any other question based on what we did yesterday? So we can start today's business. Okay, that's great. Let me just quickly do some.
No, I'm just.
Let's start.
No.
Yes.
Okay.
What I want to quickly talk about, though we have run them. If you see yesterday, we talked about the reason why this thing not coming out. I want to get that, what do I call it? Is it the touch now? Let me get the, let me, okay. Okay, I've not even shared. Did you see it? I was even thinking I was sharing. I didn't even share. Sorry.
No, not yet.
Yes, I've not shared yet. I thought I was sharing. Let me bring the annotation out.
Okay, you can see now.
Yeah,
you can see now.
Yes.
Yes. So what I want to quickly look at is, let's quickly talk about that Fisher exact. Because, you know, we have already talked about it anyway, but you know, I was telling you about the formula, but it's very useless. You don't need it, because it's just for you to know the concept. It's direct probability. It's just for you to know when to use it. And we already said it yesterday. When the expected value is less than 5 in more than 20% of the cell, or there is any one, at least one expected value, one cell with expected value less than 1. So it is believed that the chi-square is not valid. So the chi-square with its p-value, you can still put it there, but it's not valid. So you now go for Fisher exact. The Fisher exact is not a static, it's a p-value on its own. That Fisher exact is p-value directly. It's probability. No probability is p-value is probability. So the chi-square will calculate the chi-square and give you the corresponding probability. which is the p-value.
Oh,
But
okay.
Fisher exact just calculate the probability straight without any
Oh, I
statistic
see.
attached to it. That's just it. So that was just. So let's quickly now talk about the. You know, yesterday we talked about different families of different type of chi-square, different family based on the degree of freedom. We also talk about different type because there are different statistics that follow the same distribution. It's just like when you say law enforcement agency. No, law enforcement agency, there are plenty. So there are many agencies in Nigeria that are in the same, they are different, but they follow that pattern, law enforcement. So it's the same thing. Chi-square, there are a lot of statistics that follow chi-square distribution. And we said that the Pearson chi-square, which is actually used to look for association between two categorical variables or to find difference between proportion in between groups. Can be 2 groups, can be 3 groups, can be more than that. Independent group, between independent group. We say that you can actually even use what do I call it? We talk about the likelihood ratio chi-square. They will now say another thing apart from looking at association between independent groups. The Pearson chi-square also does something. It measures the goodness of fit. It tests the goodness of fit. And I explain what the goodness of fit. So that we can understand better. That's why I just want to start with that. If you look at our timetable for today, I think it starts with this good test of goodness of fit. It's still Pearson chi-square, but it's quite different. Instead of you having 2 groups, category of group is only 1 category. You are not looking at association between 2 groups or 3 groups. You are just testing. There is 1 group. You want to test it against a particular distribution. It's a single sample non-parametric test, also referred to as a 1 sample goodness of fit test. Is used to determine whether the distribution of a categorical variable, like block group now, ABO block group, you can either be A or B or AB or O for ABO system. So you want to see, does it follow an hypothesized distribution? The hypothesized distribution is just the maybe the pattern in the population. Maybe they have done in the city of Lagos now. So from years they have taken blood sample from population, already established that in the population, this is a percentage that is A, this is a percentage that is B, this percentage that is A, B, and this is a percentage that is O. It's established. So everything will add up to 100%. So in your own lab now, you now see you did your own study on your own lab. You now have a group of people, you want to be about 300 of them. You see their different block group. All those 4 they are categorized, but they are in different percentage, slightly different from what they said is in the population. You want to test, does it fit? Does this, what we are saying, that this lab, the people that come to this lab, their block group, the distribution, the percentage I'm seeing, the frequency I'm seeing, does it fit into the population? If you remember, was it last week, those people that came for SPSS training, when we talk about 1 sample t-test, you know, you are not 2 groups now, it's only 1. You just have 1 sample, but you are comparing it with 1 mean in the population. But that mean in the population, you don't have the sample for that. They have calculated before, they just saw it in literature. They just say the mean is 30. And your own, it's not only that you can know the mean, you also have the raw data for all your, maybe there are 400 people, you have it. But you are comparing that sample with just a value in the population. That's 1 sample data. It's the same thing with it. Here you have your own data, but you just only have that, this thing is distributed like this in the population. You don't have data for that one. But you have your own data. So you are comparing your data, which is 1 sample, with something that's already been published, which is believed to be what is in the that is what is in the population. I think I'm talking sense. So the expected frequency in this group, in this one is expected, is what is in the population. It can be equal, it can be unequal. I will discuss that. Now, as an example, I have an example. If you look at the set, the socioeconomic class, I put the block group there. I also send socioeconomic class too. Dr. Yemi, did you see you can download it because we use it. I asked Dr. Balogun to download it.
Yes.
Look at the same socioeconomic class, SEC. They are called SEC too. I added something to it. Please download it. You are online. Just download it now.
I've downloaded it.
You have downloaded it, right?
Yes, let me look for it.
That's great. That's great. Please, anybody that can download, just download and have it so that we can discuss. We can use it to do some analysis because I added one variable to it.
Yes, I've
socioeconomic. We are now have socioeconomic class before COVID-19, then after COVID. Just I will explain the usefulness. So look at this example now. The blood group, the table below shows the distribution of ABO blood group in the tertiary hospital laboratory and the expected frequency in the population. Can one infer that the distribution observed in the hospital significantly differ from that of the population? You see, what I'm saying is that look at this table, observed value, you see that ABO, AB, AB, and O. Look at the number. There are 300 people. Look at the number in each category. And if you put in the percentage, look at the percentage. And look at the percentage they say is in the population. That's the one in the orange now, or whatever. In this light color. Can you see the percentage distribution in the population is slightly different from that of your lab? Can you see? So you still want to see. So your own percentage now and the value is what we call observed value. Observed pattern. The one in the population is the expected, because that is the one that you expect this one to be. That's what they tell you is in the population, that is the expected. The one you have now is observed. But can you see now, it's not two groups now, you're just comparing one group with a result which is in the population. So it's the same, look at it, the same formula. It's just for you to, okay, the only thing, how do I calculate the expected now? How do I calculate? If you look at it, in your own data, you have the frequency, you have the percentage, but in the other one, they didn't give you the frequency, because they will not tell you the sample size, but you only have the percentage. Whether they use 1 million as sample size before or they use 200, it's not your business, but that is the percentage they are giving you. So how do you now calculate the expected frequency from that? So you're going to calculate it based on your own sample size now. If you look at it, the table, this second table, incorporate that. Just like the way we did it before. Look at it. For you to calculate, the sample size you have there is 300. And the percentage in the population is 20, like for A now, this is 21.1. That is 21.1% means 21.1 out of 100. If you have 100 people, 21.1, somebody is asking a question. Somebody ask a question?
No, go ahead.
Okay. So out of 100 people, 21.1 has blood group A. That's what it means. So you have to say 21.1 over 100 times of, that is times 300, because you want to apply it to your own sample size, which is 300 now. So that is, if that same particular thing is applicable, is applied to your own sample, what percentage is supposed to have blood group A? Or what number, what frequency? We already have the percentage. What is the frequency? How many people will have blood group A? That is the expected frequency. Look at it. We have calculated for all of them. So if you look at it, it's not quite, the difference is not much from the chi-square for independent to test independent. And you see, it's the same formula. Expected observed minus expected square over expected for each of them, the category. When you do, you add it, it gives you the chi-square. And the degree of freedom, you can see the degree of freedom is the number of sample minus 1.
3.
So the degree of freedom here now is 3. Because what is it? You have only one sample and there are only 4 categories. So is n minus, if you have 4 categories, that category minus 1, that is the degree of freedom. So there are 4 categories, and 4 category minus 1 is the degree of freedom is 3. 4 minus 1 making 3. So I want us, I don't know if few people have read it. So Dr. Balogun, please, if you want to answer me, you have to unmute yourself. I will not hear you unless you unmute yourself.
Yes, I'm
Okay,
here.
Doctor, yes. So you have downloaded that sec too, right?
Yes.
You know where you save it, okay? Before we are going to run this because this thing is there, this blog group is inside our file. We want to run it. I want to ask question. Does anybody have question before we go and run it? We want to run the same thing with SPL. You see the way, because the way it's being run is different, quite different. It's a little bit different from the way the other one is run. If you look at the previous slide, I said the last bullet point here in this previous slide. I said the expected frequency of each group of the categorical variable can be equal or unequal. What I mean is that sometimes when you are testing your hypothesis, it may be that you expect the different four group to be equal. That is, each of them should be 25, 25, 25, 25%. It may be, because sometimes what you are testing may be that, oh, different categories should be equal. That may be. Or it may be that there is a particular frequency. In this case now, there is a pattern, particular pattern we want to follow. But in some situations, it depends. It may be that maybe you expect, it's just like you have in a school where they have one secondary school, class 1 to 6, and they add an event, inter-sport. You expect equal proportion, that is, all the people, the percentage of the people that came, they should choose equal number of people from each class to participate in the entire sport, from each level rather. So if you want to compare, okay, in this school now, you now look at the total number of people that participated in entire sport. You now divide, you now try to know what proportion is from each level, class 1 to 6, DSS 1 to SS3, what proportion. So you can have different proportion. You want to test against equality, that is, your expected frequency is that all the people that participated, they should be equally distributed. That is, if you divide them into 6, one part should be from class 1, 2, 3, 4, 5, 6, like that. In that case, you are testing that one against the expected, which is supposed to be equal. But it will not be like in this block group now. You don't expect, because in the report, like the block group is not actually the ABO group, the 4 categories are not equal in the population. So you have your own expected frequency. So that's just what I want to say. No, if there's no question, let me stop sharing. Let Dr. Balogun share that thing with us. Because I want everybody, I want you to be participating, because I don't want to be running it, because I will tell you what to do, but by the time you do it yourself and other people watching also. I was telling somebody, a friend of mine is supposed to join, Dr. Lon Femi. He usually does training on starter, and he was skeptical if you can run analysis on Zoom. I said, why not? So he wanted to know, he said he would join. I sent the link so that he joined and see. So, and I told him one advantage of Zoom over the physical training is that in physical training, if somebody is running analysis like the way Dr. Balogun want to run now, I can only go to his table and see his this and say, oh, this is what you are running. Oh. But now in Zoom, if it's wrong, everybody will see it.
It's true.
In the physical summit, it's only the facilitator that is projecting. You cannot, it's not easy to be changing code. You are changing code, okay, this person want to, let's see, is projecting again. No, you will know how, but on Zoom, once one person is demonstrating, everybody will see. Can you see the advantage? Okay, Dr. Balogun, share that file.
You have disabled my screen sharing.
Sir? Okay, yes,
You
sorry.
disabled my
Sorry. I've not opened it. Wait, you can share now. Sorry. Dr. Azana is on and off again. It's internet of a thing. That's great. I think everybody can see. If I can see, everybody can see, because it's not me that is sharing. So what we want to look at now is the blog group. You can see the blog group. So what you did, Dr. Balogun, go to view. Okay, go back to that data window. Data window. Yes. Go to view. There's a view at the top left corner.
Top. Is the
View
third
after
icon.
edit.
The third icon,
Click
the
on
third
it.
icon.
Go and click on that value label, because it's you that want to click on yes. If we demonstrated it the right time. The labeling you want to click on later that show. If you don't want to say, so what I just want us to, okay, there's no even need set. You can return it. You can return it, don't worry. You can return it. You can return it.
Okay.
No, it's seeing your this thing. You can return it. No, it's view. Value. Go to variable view. Yeah. Look at the block group. You can see that click on that value. I've coded it. Click on the value under value for block group. Under the value. Column value. Open it. Yes. You see that I've coded. If you want to do this, you want to run this goodness of it. It's good for you to have coded it. The reason being that because you need the order, the way it is ordered. You need to 1, 2. So A, I put A as 1, B, block group B as 2, A, B 3, and O 4. It's good. So close that thing. It's good for you. You know the way you do it. So let's do the analysis now. Go to analyze. You will see you are not going to because I said yesterday anything chi-square you go to cross tab because it's categorical. Because this one is not dealing with 2 categories. Cross tab has to do with two group or 3 group. You are dealing with many groups. Two variable in 2 samples rather 2 groups. But here calculating 2 variable. Let's say 2 variables. Somebody is talking. Is there any question? Now, here now, it's only 1 variable. It's like some people have question, right?
No, Masera is just coming in.
Okay. Zainab, welcome. Okay, now, Dr. Balogun, you now go to non-parametric text. You know, even chi-square is non-parametric text anyway. Go to non-parametric, it's not frequency you are going. It's not descriptive, go to non-parametric text down. It's down, yes. No, it's in midway. You have already non-parametric test ahead. See, go down. No, not generalized. Non-parametric is down. Yes.
Yes.
Then now go to legal value, legal dialogue. Then you see chi-square there. Click on chi-square. Yes. So now, if you remember the other chi-square we are doing, you go to constability. Actually, chi-square is not parametric. This is where it's supposed to be there because it involves cross-tabulating a two variable. That is why they imagine with any other thing can do with that. But here, this one does not involve cross-tabulating. Welcome, Dr. Ajara. So this one does not involve that. That is why you now come here. So move that block group. Move it to the test variable list. Block group. Dr. Balogun. Dr. Balogun. He's not hearing. Move the block group. Hello? Doctor, can somebody hear me? Busola, can you hear me? Dr. Yemi, can you hear me?
Okay, I thought it was my end.
Hello?
Yeah.
Hello, yeah.
Yeah, you are back.
Yes.
Hello? You couldn't
Yeah,
hear me,
hi.
right?
We are hearing you now.
I don't know, is the internet, God will help us. Internet that they say is unlimited. Pay for unlimited, smile. Unlimited means, big bundle is unlimited. You pay daily for it and it just say it is low. Okay. I said that, okay, you have moved it.
Yeah.
So now you will see all category, expected value, under expected value. You are not using range now. On the go down on the right side, you see expected value. By default, what is there is all categories equal. If let's say all categories equal, you just assume that those 4 groups, you expect it to be 25%, right? That is what you now do. We don't even, before we even came here, did you write down what are the expected count? I know that is 63. Okay, what you can do on stop sharing. Stop sharing, Dr. Balogun. Yeah. So let me just share. Somebody sent chat. Having network challenges. Is the internet? Yes, what I wanted to do here is for us to see, okay, I didn't copy. You need to know the expected frequency count because you're going to enter it there. The expected count. Can you see it now? This my camera. The expected count for is 63.3, 56.7, 46.2, and 133.8. So that you are supposed to have it. Okay, let me stop sharing now. Dr. Balogun, share. Share, Dr. Balogun. Dr. Zainab. Dr. Zainab, welcome.
Thank you.
Yeah, welcome. Okay, so Dr. Balogun, now click on values.
But at least I'll follow it.
That's great. Please no, go down on the right side. You see, instead of all categories. If let's say all categories are equal, that is, each of the block group you expect to be 25%. That is, they should be equally divided among the 4 categories. That's why you just do all categories equal. But this one, all categories not equal. So you start with number 1, A. The first one, you have to. That is why you have to know the order. The way you code it. You know, A is number 1. It's 63.3. Put 63.3. The count is supposed to be 63.3. Hard. Click on hard. So the second one is 56.7. The count for the second one is 56.7. Hard. Can you see it's added down now? The third one is 46.2. The last one is 133.8. Click. Okay. So share your share your result view with us.
Output window.
Yes, output view. Yes. Can we see? Can you see now? You will see something. If you look at the one I calculated with and we didn't talk about it, I will calculate it with that. If you see, it's the same thing. The expected, look at the expected count you put. Look at the residual. That is, when they remove the expected from the observed, you know, since observed is more than expected, it will be positive. It will be positive in half, it will be positive, negative in the half. Can you see? If you look at it, look at this one, it's negative here, it's negative on this side, it's positive here. So at the end of the day, the chi-square is 40.464, and the degree of freedom is 3, because the 4 category minus 1, 3. And 0.0 is 0.02. It's significant. So there's a significant difference in this group and the one in the population. There's a difference. So you cannot say that group represents the population. There's a difference. That's what the result is showing us. So you can share. I don't know if there's any question. You can stop sharing. That's how to do goodness of it.
Yeah, my question is, you know, the SPSS default is all values. That's the default.
No, the default is just good is that all what it means that, you know, I told you there are 2 options. It's either that you expect all value to be the same, that is, it's the equal proportion in each category. It's not like if the block group now, what we expect is that 25% should be A, 25% should be B, 25% should be A, B, and 25% should be O. If that is what we expect in the population, that's what we just leave it like that, just run it. Okay, we'll go back and run it like that. You will see, but that's not the way it is. So when you are testing now, it's two ways.
Yeah,
sometimes what you are testing is supposed to be you expect it to be equal. So instead of you wasting time to be typing 25, 25, 25, you just say all the cases, you just do it for you without wasting time. But if it's not the same, you now put the expected counts there. I don't know if you understand what I'm saying. I don't know why I cannot see. Is it that my internet, I cannot see? Okay.
The expected count we did manually. Does it mean one has to first of all do it manually? Because we got the expected count by manual calculation.
Yes, that's what he's telling you. You have to do that. You know, you have to do it here. It's a good question because the other one, you know the reason is like that? Because you don't have data for the one in the population. You know, the other one we don't do manually is we are comparing two groups. We are comparing two variables. So you have the information with you. But in this case, you don't have the information with you. They just give you a summary of something. Okay, they give you a percentage. They say blood group, this is 40%, the blood group is 25%. But we don't know when they did the study, what is the sample size? Is it 1,400? And what is the count percent? We don't know. You just know the percent. How do you use percentage alone? Well, 20%, maybe they calculated it from 1,500, or they calculated it for 40 people, from 40 people. We don't know. So you have to now apply that that percentage to your own sample. If you are to apply the percentage to your own sample, what is this count it will be? Because in our own sample now, we have 300. 300 people, our own sample size here is 300. So we apply that expected to that 300 to see if the percentage that happened in the population is applicable to our own this sample, what will be the count? Does it make sense now? So yeah, you just have to first of all do that. The issue there is not that if you look at the expected per se, it's not as if you are calculating per se. We are calculating the count. They have already given you the percentage. It's the counts you are just bringing out. And let me tell you, if it is the other way that is equal, you don't even need to calculate anything. You don't need to do it. If you assume, you expect that attribute should be equal, evenly distributed among the different categories, you just go straight. You don't need to calculate. If you look at it, you don't need to calculate the expected or anything. You don't even need to have any figure. You say that when it says equal, that should that if there are 4 categories, that should that is 25, 25, 25, 25%. You don't even need to calculate it. You just go there, you just create all categories are equal, just run it. In that case, you don't need to calculate any expected. But once it's not the same, you need to have their figure and now factor out the count. Welcome, Dr. Ogbu. So, Dr. Isaac, you have a question. Go on.
Sorry, my laptop, there was a power problem. So I'm sorry to take the group back. I lost you at that click non-parametric. I don't know whether people can help me because I missed my
anyway,
thing went blank.
He will do it again. He will do it. He will even want to repeat it and use all this because of question somebody was asking.
Click non-parametric.
Don't worry, we'll do it again. I even wanted to go back there to demonstrate another thing. Okay, Dr. Balogun, if there's no question, let's share again. Let's do it again. Dr. Balogun, share again. Let's do it again. Dr. Balogun.
Yes, I'm here.
Okay. Help us share, please. Sorry for stressing you.
No.
Okay, so let's go to the way you go, analyze. Now go to non-parametric. Can you see now? Under a legal dialogue, you see chi-square there. Can you see Dr. Isaac? So what you can do, anyway, we are recording you still see it. Go on, sir. Click on chi-square.
Okay.
Click on the chi-square.
Yes.
Yes. Now, look at it. Now, what we did, Dr. Isaac, was to enter the expected count we are calculated. As you are entering one by one here, you have to handle the way you code it. You know, we code it 1, 2, 3, 4. You have to, if you don't do that, it will miss it. Because the one that is number 1, the coded one should be the one you enter first. And it's A, B, and O. That's the way we enter the block group. So that's where we enter their expected value also. Now, let's say, click on the all categories equal, Dr. Balogun.
All categories equal. Okay.
Click on it. Click OK. Let's see. Run it. You see, it will give you different results. Share the result view.
Give us a 50 something. Uh-huh, 51.
Can you see? Can you see that it's different? Because it tell you, you know, there are 300, the sample size is 300. If you say all of them are equal, there are 4 categories. That should have, each of them is 25, 25, 25%. And 25% of 300 is 75, 75, 75, 75. So here now the residual means the difference, the deviation is the residual, the difference between the observed and expected. I put them here. And if you look at it, we have been saying it before. When you add the positive and negative, they cancel one another. Can you see? -1 plus 1. Unless if you any deviation like that, they're like that. Can you see? It's more significant, but that's not the blood group is not like that. The blood group is not, we don't in the real population is not equally the percentage is not equal. Most of about 40% is O. It's 20-something% that is A and all those ones. So 40, most people have this O. So this is what you are sharing with us, Dr. Balogun.
Yes.
You are sharing your
sorry.
Your literature.
Sorry.
Your what you are reading.
Sorry.
No problem. So you can stop sharing. When you stop sharing, the thing will leave. Okay, I think we are done with that. No much. Is there any question concerning? If you look at measure of goodness of it, that is how to do it. Very simple. Measure.
So what's the conclusion now?
Oh, conclusion.
How do you conclude
don't worry.
this?
Let me share my this because the conclusion. If you look at it, look at what I'm sharing. If you look at the slide, using hand to calculate it, if you look at you got the same value. It's the same. The conclusion now is that for the degree of freedom of 3, the critical value for chi-square for the degree of freedom of 3, I think it's around 7.99. So 14.464 is significant. It's higher than critical value. And what Dr. Balogun run for us, the p-value is 0.002. It means that the blood group we are testing against the population, so they are quite different. The distribution of the blood group in that laboratory, in that teaching hospital, is quite different. It's not a representative. It's not representative of the population, and we expect that teaching hospital is not a representative of the population, because you know what I mean by that. It's people that have problems that go to the hospital, especially their problem is more. That's why they have to refer them to teaching hospital. So you don't expect the blood group of people that go to teaching hospital that they did the investigation for the laboratory to be the same thing to tally with the population scope. So does it make sense, sir? So let's continue. If there's no other question, let's continue. Now, let's look at McNema. No, yesterday we we analyzed this piercing, look at gate correction. We talk about the Fisher exam, which I just showed you the formula now. We also look at the likelihood ratio chi-square. So we just finished discussing the measure of test of goodness of fit using piercing. Now, piercing look at independent group. That is looking at measurement from different groups, like the one we did between male and female employment rate. They are different groups. But this McNema, when you take a measurement before and after me, you take measurement for some people, you also take for another people. Let's just look at example here, because it is easily understood by looking at example rather than just talking to the Look at this. Look at example below. It shows hypertensive status of group of adults before and after an intervention that involved lifestyle modification. Did the intervention significantly influence the hypertensive status? Look at it. Hypertensive before, maybe they gave them some life modification, training, exercise, diet, and many things. They measured the blood pressure of these 200 people, they are 200 in number, and they classify them as hypertensive. Look at the inception. 60 were hypertensive and 140 were not hypertensive. Now, after the modification, after some months, they came back, they measured their blood pressure, they classified them to hypertensive and non-hypertensive. They now got that 40 were hypertensive, 160 were not hypertensive. You can say there's an improvement, because before 60 were hypertensive, 40 were not hypertensive at the section. 20 is out. But you cannot really say, unless you put it to test, to really show if this thing actually, this modification, the intervention has actually reduced hypertension. Because it's not as if maybe it's from all the 60 that are hypertensive, that were hypertensive, that 20 people just drop, no more hypertensive. No. You can see from the table, 8 people were hypertensive before and they were still hypertensive after. 52 people were hypertensive before, they were no more hypertensive. 32 people were not hypertensive, they became hypertensive. The 108 people were not hypertensive, they were not hypertensive also. So you see that some people move from, some people stay where they are. They were hypertensive before, they were not, they are still hypertensive. Some people were not hypertensive before, they are not still hypertensive. But some people move from hypertension to non-hypertension, while some people move from non-hypertension to hypertension. Can you see now? So you need to put it to test. The logic behind it. So let's quickly discuss it. Now, I think the next slide, the way it works. If you look at the table, observed value, it's the same table I just repeated here, that observed value. You see that I highlighted some red. So this one I highlighted, they are what we call discordant. Discordant. The other one are concordant. You know, when we are, this is 2 by 2 table, and we don't consider the total, all this total around. But if you look at it, the concordant are yes. Someone that was hypertensive before, and he's still hypertensive. That shows that he didn't move, there's nothing, that thing didn't change anything in that person, those people. They are out of the analysis. Then the 108 were not hypertensive before, and they are not still hypertensive. So they didn't move from where they are. But the people that are concerned, is you are concerned with, are these 2 groups of people. The first group, they were hypertensive before, they became not hypertensive. This other one, they were not hypertensive, they became hypertensive. And maybe saying that we have more of them that become not hypertensive. But if the no hypothesis you want to test, you want to test it from this discordant. Look at what I wrote here. The first, the no hypothesis is that B is equal to C. What if actually, because the no hypothesis will say that the intervention has nothing to do with hypertension status. That is, the intervention has not influenced hypertensive status. That would be the no hypothesis. Why the alternative hypothesis that, oh, the intervention has affected the hypertension. The intervention may even make the hypertension worse. It doesn't, that's what we are talking about today here now. The intervention can improve it, it can make it worse. We don't know. So, but the no hypothesis will say intervention has not influenced it. The alternative hypothesis will say hypertension, the intervention has influenced it, whichever way. Now, if truly no hypothesis is true, So if the number that move from yes to no, for hypertensive to non-hypertensive, should be equal to the number that move from non-hypertensive to hypertensive. So B and C should be the same, if not hypothesis 2. That would be the expected value. The expected value, it should be the same for those two cells. So now the logic, what it means is that for you to now know the expected value now, you now add B and C, you divide by 2. So that's why you say B is the B should be, the expected for B should be B plus C divided by 2. The same thing for C should be B plus C divided by 2. That is when you add the two together, when you now divide by, look at it down, that's what I done the expected value. You now add the two together, you divide by 2. So you expect 42, because when you add 32 to 52, it gives you 84. Divide 84 by 2. So it will be 42. So you expect, if no hypothesis is true, the expected value should be 42 should be equal for both of them. And if you now come and now apply the what do I call it? The chi-square formula, just directly to only those two, because look at the two you are involved, those two cells. Look at if you give you the, or intelligent people, they now find out, instead of wasting time, they discover in the process of calculating it that just say B minus C square all over B plus C. If you do it that way also, it gives you the same answer. Can you see? That's why the McNamara is so simple. B, that discordant cell, the difference between them, square it, divided by the addition of the discordant cell. It gives you the chi-square, the McNamara chi-square. It's as simple as that. But for 2 by 2, for 2 by 2 table like that is, because we are having two categories of the outcome. That's why it gives you the 2 by 2. When you measure it before and after. Actually, the machine does not actually calculate. I have not seen any machine that calculate the chi-square. They will give you the p-value. But we are going to look at other one when the category is more than 1, when more than 2, 3, 4 like that. That one, we look at it after this one. That's McNamara-Barker test. No one lady was asking me the question on Thursday. Is it Thursday or Tuesday? I don't know which of them. Thursday, about it. And I said that. And I said that I will discuss it in these weekends. I even sent test to her that you should join, because I'm going to elaborate on that Barker. We're going to look at it. Before we go, I don't know if there's any question. We want to go and run it. Before we go, any question on this?
Go on.
I should go on.
Yeah,
is that the consensus? So it's well explicit. Okay. So if you downloaded the hypertension before and after, somebody should go and read it and share with us. Let me after hypertension before and after. There's a folder, one of the folders I sent to you. Hypertension before and after. Hypertension before and after. Nobody is there. Who? Zanab. Dr. Zanab. Dr. Zainab, if you want to answer me, you have to unmute yourself, because I will not hear. Dr. Zainab. Okay. Doctor, you are not answering. Okay. Dr. Zainab. Okay, Dr. Yemi. So you have shared. Sir. Okay. Yes, go to analyze now. This has to do McNamara chi-square. Analyze. Is this crosstab? Go to descriptive crosstab. Now move before. If you want to say row and column, before should be the row and the after should be the column. Okay. Hypertension before.
Really?
Then move it in, yes, under row. Move it to the row, the other one to the column. Click on statistics. You see McNamara down under where kappa and risk is. Yeah, down here. McNamara. So you know, it's not pressing chi-square you are calculating. If you go and click it, put pressing chi-square for that thing, assuming that that's what you are doing. But you know, the computer is garbage in, garbage out. It doesn't think for you. Okay, continue. Okay. Okay. So share your result. Share your result view with us. Yes. Can you see the same table, but you see the p-value 0.
Yes,
0. Scroll down. The p-value is hiding. Yes, thank you. 0.0338. But it didn't give you the statistics. As simple as the statistic is, just say b minus c squared all over b plus c. The computer cannot do it. The logic is beyond the computer to bring it out. But, so you can use your hand to calculate, very simple. But you cannot calculate the p-value, so the computer gives you the p-value. But the one you can calculate, so you provide it. So you and computer, you are partner. That is it. Any question? So we want to go to, this one is just 2 categories. Now I want to go to the one that has 3 categories. And that is why I asked her to go for that set 2. Any question concerning this? Dr. Ogbu, Illumina, unmute yourself if you want to talk. Well, not yet. Yes. Did you download those the file?
The second one you sent, but the first one I was not able to download it.
You downloaded the second one.
The second one, yes, but the first
the
one.
The one I just sent when I'm starting the meeting.
2 days. No,
I'm talking about those data file that we are using. All these data files. Have you saved them?
I have not saved them.
So because if you don't save them, then I want everybody to be part of what we are doing. So Dr. Zainab. Dr. Zainab. Don't answer. Okay. Let's look at Dr. Yemi. Stop sharing. Stop sharing. So no question about this, right? So
no.
Okay, it's very simple. That's good. Yes. Now let me proceed. Now let's look at McNamara Barker. The one we just did now is, if you look at it, we have only hypertensive, yes, no. But there are some things you may have up to 3 categories. No? And it's before and after. So as the category is becoming, it look more complex. See, though it's just for you to understand the concept, because when you run into the computer will give you, it's just for you to know where to press. But all this one is just for us to just talk about. In fact, I will just keep this place because I don't like talking to the moon. I prefer pictorial. And when I share, you see it, you can look at it if you want to read this one, the materials. But I like illustration, something that will illustrate. But if you want to, all of them will have the complement. Look at Honorable Loguna, his opening book, reading. It's not everybody that will read like that anyway. But it's good to read and look at everything. So when you look at it from different angles, you'll be able to understand. So if you look at it now, example I give here, it's just like, look at upper, middle, lower, upper, middle, lower. So we are looking at socioeconomic status before COVID-19 and after COVID-19. You know, after this COVID-19 now, people will change position. So people that are rich before, their business are going to crash and they may not get themselves. While some people that were not making it before can make it. Like, no, those people that are selling food now, they are the one making it. Whereas the people that are collecting, the people that are collecting salary for government is still giving them. But the people that are doing work on their own, they are the worst hit in this COVID-19 because of they cannot do their business and they are not getting salary from anybody. And people that are employed in the private sector also, they retrain them if they cannot pay. What will happen? So what we are just saying is that before COVID-19, we have the socio-economic status. After COVID-19, some people will still remain where they are. Some people may change. This is an example. If you look at it, this upper, these are the people, all those whites, that's the along the diagonal, you see the concordance. the concordance along the diagonal, and we don't use them. We don't use the concordance. The one that was upper and upper before and upper. The one that is middle and middle after. The one that is lower and lower. The thing did not affect them. But the one that are affected are the one that are off the diagonal. And when you see the off the diagonal, for this 3 by 3, because this is 3 by 3 table, you will see that there are 3 pairs also. 3 pairs. I coded them, deliberately coded them with the same color, the pair. Look at this one. I don't know which color is it, maroon or whatever. This color that look purplish or whatever. You will see that the person was upper before he become middle. These people. But there are some people that were middle before they became upper. Can you see? So upper before become middle and middle before. So exchange between middle and upper. That's what that one is saying. The green one is the people that were upper that became lower and people that are lower became upper. The exchange between lower and upper. That is the green one. Then the blue one, light blue one here, is the exchange between people that are middle and became lower, and lower became middle. So exchange between lower and middle. Can you see now? So we have 3 pairs. Unlike when it is 2 by 2 table, there is only one discordant. But here now we have 3 pairs of discordant. And those 3 pairs, all we need to do is to, if you put, all you need to expected, how do you calculate the expected? That's what I did here. Very simple, the same thing. Because if the null hypothesis is true, the people that move from middle, upper to middle and middle to upper should be the same. That is, you add them together and divide by 2. So for each of them is half of the addition of them that are the this thing for them. The same thing for this one, the same thing for this one. If you now calculate the expected value out and now put it in the formula here, it will give you this answer it will give you. And if you use the other formula where you just say this minus this divided by the addition, both of them, any one, it will give you the same answer. That's just the logic. So let's just run it. And here the degree of freedom is K. I think I put it in that K, which is the, if is K by K table. That is, because it has to be K by K, because you know the T category, when after also it will still be the same T category, it's going to be 3 by 3. So that K would be, the degree of freedom would be K bracket K minus 1 over 2. Like this one, 3 bracket 3 minus 1, which is 2. 2 times 3 is 6 divided by 2 is 3. So the degree of freedom here is 3. So the person that have read the socioeconomic sec 2, please share with us. Read it and share with us. If you that have downloaded it, the one I sent today, share with us and let's just run this. You will see. Let me unshare rather. Stop sharing. Yes. Okay, who is sharing with us? Or if there, before we do that, is there any question before we run the analysis? Is there any question?
Yeah, Dr. Lolapo, I think I would say I'm a little bit confused.
You are a little bit
confused about how you even arrive at your table before and after.
Okay, don't worry. Okay, ask your question.
Before and after for the bulkers and even for the basic.
Okay, but what about the McNeman? That one's okay, right?
Yeah, this other one that is more than 2 by 2, like 3
what
by
did
3
you say?
contingency. How do you get the values before and after? I can't. I'm
okay, don't worry.
to read.
Okay, you have the data now, right? Read the data. I want to show you on the data on the SPSS something to show you before I will come back to my slide and explain. Please, if you have read the data, bring the data out.
Yes.
And share with us.
You want me to share? Okay.
You have not. The you have downloaded. You know where it is now. That's set 2. Yes, thank you.
Okay.
So what if you look at what we just did, that you see, check before COVID. This is the value for each person. There are 300 of them. Look at this person now. Before COVID, the first one you see on this place. Before COVID is lower. After COVID is still lower. Someone was middle. The second person was middle, but it became lower. This person was middle, became lower. You see, some people are middle, they became middle. This one was middle here, became, this one in line 13, became upper. Can you see? So what we're just saying is that the category of socioeconomic is not true like the hypertension, that is yes or no. Whenever the category is more than 2, that is where the banker came in. The category is 3. It can be 4, but this one is 3. Once it's more than 2, it will know when when it is 2, you constabulate. It will be 2 by 2 table. Yes or no, yes or no. But when it is 3, it will show the 3 vertically, show the 3 horizontally also. So when we now cross, okay, it's better. Okay, run it, let's run it. Go to analyze. Let's just do it now. Once and for all, I will explain the table. Because the table is going to bring us the same thing. What do you say?
Yes.
It will show the
Can
table.
we make the table first?
No, don't worry. It will bring the table out. Don't worry. Just bring it. The same table will come out. I will go and share. Don't worry. Just cross tab.
Okay. Row.
So row will be before. Okay, yeah. Put before as row. Sec before. Column. Sec after. Okay. Then go to statistics. Statistics. McNema. Is McNema. Even to his backer, I will give you. Is there? You're on? Okay, yes. Continue. Okay. Okay, share your result view with us.
Can you see it?
Yes, you can see. Yes. So I will go to but it's the same thing on my table. I will go back. You will see what I just want to say is that for the before it leaves them upper, middle, lower. That's the way we arrange. And it arrange it here also. So all is showing you, it will show you this one was upper before, upper after. This one is upper before, middle after. Upper before become lower after. This one middle before, upper after. Middle before, middle after. Middle before, lower after. This one is lower before, upper after. This is lower before, middle after.
Can anyone hear me?
Eh?
Yes,
now,
sir.
Can anyone hear me?
I can hear you, sir.
I'm hearing you. I'm hearing. Because you can hear me now. Now, you will see. Okay, let me go back to my DC. Let me go back to my own. Let me share. So, can you see my own now? Can you see my own? Can you see my slide?
Yes.
Please, I want you to respond. Can somebody see my slide?
Yes, I can see your slide.
Yes, because if you don't unmute yourself, if you are talking, I will not hear, I will not know. Okay, now if you look at it, it's the same thing you just run now. Welcome, Dr. Lofemi. It's the same thing you just run now. I put here, if you look at it, the same figure. I just, along the diagonal is the concordant. Concordant means when somebody that is in the same state before and after. This first one here, 6. Be upper. Yes. It was upper. Those people that were upper before, after COVID, they are still upper. These 36 are the ones that are middle, they are still remaining middle. Then these 93 are lower, still remain lower. All these other one off the diagonal, and they are the one that change one way or the other. And the change also, because it's 3 by 3, it's not 2 by 2. The change, if you look at the 2 by 2, the only 2 cells change. But in this one now, 6 cells change. Because the total cell here is 9. In 2 by 2 table, the total cell is 4. And we have 2 that didn't change, 2 change. But here, the total cell is 9. 3 didn't change, then 6 change. All those ones that are along the diagonal, they didn't change. but off the diagonal on both sides change. But they change, they are reciprocal, the change is reciprocal. Look at this 14. These 14 are the people that were upper before they became middle. The corresponding group are the people that were middle before they became upper. That's the 7. That's why I painted them the same. Those are the ones that change. The corresponding change. So if no hypothesis is true, if the COVID-19 didn't affect them, what is the expected value? So the expected value would be that both of them should be the same. Because the people that change from upper to middle, should be equal to the number of people that change from middle to upper, which is the 7. These 14 and 7 should be the same. If they should be the same, so for the expected value, all you need to do to have 7 and 14 divide by 2. Whatever you get, you give it to each of them. Yes, I mean. So it's only that I didn't complete it here. 14 plus this will be 10.5. The expected count. I didn't just complete it there. Maybe if I so sorry. What I wanted to do is to let me share so that I can tap on it. So that shows that it will be 10 point. So the value will be there. 10 point. I didn't just put the value there, but that's how you get the expected value. I don't know if you understand it now. I want to discard it. Dr. Balogun.
Yes.
Do you understand now?
I'm with you.
Yes.
Yes,
now,
I understand the table.
Yes.
Now.
If you now look at the second one, the
table.
The green, yes. If you look at the green now, you see that the upper that change to lower, upper before become lower, the corresponding group will be the lower before that become upper. That's why I put both of them. So both of them should be the same. So the expected value will be, you add the both of them divided by 2 for each of them. Then the last pair would be the people that were middle before that became lower. And the corresponding group will be the people that were lower before became middle. Are you see now? So both of them also. So if you calculate the expected for them, you use the formula for normal, even the basic, it will give you the value. If you now use this one that say minus for each of them, just say all you need to add it together. You say this times this minus d divided by this plus this minus this divided by this plus this minus this divided by this. If you use this formula, it will give you the same value. And you're going to give, if you look at what you got, it's the same thing. It will give you. So the working, the understanding is just for you to understand it. I will know that it's the computer that will run it for you. I don't know.
The way you can. Hello.
Yes, sir.
So the way it's only in 2x2 contingency table you do column total, row total.
No, I don't understand. What did you say?
Overground total for. Is it only when you are dealing with contingency table that you use row total multiplied by column total over
for the expected value, right?
Yes.
For the expected value, right?
Is it only for 2x2 contingency table?
Listen to me. Is it not for to calculate the expected value? You are asking that question in respect of calculating the expected value, right?
Yes.
Yes. So now it's not the 2x2. We are going to run 3x3. It's the independent. Whenever you are dealing with piercing independent group, that is what you do. But this one is peer group. You don't do that with peer group. I don't know if you understand. This is before and after. This is that's the difference.
So how to calculate expected value for peer group is different from when
exactly. It's not The other one is for independent group. That's the row total, ground total. But this one, this is the logic behind it. If you look at it, you don't even need everything. The one that doesn't change, you don't even use it at all. It's the one that change that you use.
Okay.
It's the discordant cell you use. You don't use concordant cell. Yes, I mean now.
Thank you.
Yes, that's just the logic. I don't know if there's any other question. There should be question because if you are not asking, because the person that is asking question, it shows that he's following. He's reasoning it out. That's why he's asking question. If you are confused, you will not ask question. Yeah, I don't want you to be confused.
We are following.
Also, we
are following.
Okay, we are following.
Because we are subtracting what we expected, the expected value, we have to subtract from the original value in that cell. The value in the expected to subtract
Yes,
from
that's
the
one
original
way.
value in the cell.
Yes.
So then we use the chi-square formula. Though they have another formula here given McNemas. Then we sum the total and we'll get the same thing.
Exactly.
So for each cell, even if there are 6 cells, we get the expected and we do the sigma for all of them. Observed minus expected, observed minus expected. Because we know the percentage, we take the total number. So we are following. That's why we are quiet.
Okay, that's great. Okay. You talk for yourself because you are in your location and somebody is around about 1,000
No, I've been with you. I've been with you before.
Thank you.
When you came to Inagua.
Okay, that's great. Okay, thank you, sir. So any other question? No question, right? Okay, we continue. Okay. Let's run the
But there's one question though.
Okay.
But there's one question.
Okay.
This non-parametric, when we are doing goodness of fit,
okay,
we decided to go to non-parametric. Why didn't we go to parametric? Is it not a normal distribution, the goodness of fit?
Okay, you know that non-parametric is for something that is not normally distributed. Like chi-square is non-parametric test now. You remember?
Okay, yes, the curve, yes, the curve.
Okay, don't worry. I will ask who did it for us? Is it Dr. Balogun or Dr. Who shared that?
No,
Somebody
yes,
can share.
True.
Let me go back.
True.
So, no, I want to go back there. I want somebody to share his own, not necessarily the person. Dr. Obu. So you don't have your SPSS there? Dr. Zainab. Dr. Zainab. Hello, now. Well done.
Hello, sir.
Yes.
Sorry, I've been a little unstable, my network and some other things coming late for some reasons.
Your computer now? Okay, do you have do you have this any of the file you have downloaded them now, the data file? You didn't download them? Hello? Okay. Dr. Yemi? Okay, Dr. Balogun. Please share that file with us. The last one you shared, just share with us. Let me just explain something. We leave that. We go to other things. Dr. Balogun. Dr. Balogun. Okay. Okay, thank you. So I want us to look at, I said something. I said that whenever you are doing chi-square, because it has to do with categorical variables, so the issue of contingency table comes in. So one variable will be on that one side, and that variable will be on the other side. Okay, somebody say you can hardly hear. What happened? Which slide? I can't hardly hear. Sorry about that. You could start your phone. Okay. Dr. Yemi, unmute and talk, please. Unmute and talk. Can you hear me? Hello? It's cloudy. Okay, it's cloudy in some places. That was what happened in Anambra. It's now happening in Abeokuta. Okay. What I was saying is that for...
Sorry, sir. Sorry.
Yes, can you hear me?
I'm trying. Yeah, there are noises where I'm trying to move around to get.
Okay, sorry.
Yes,
okay, anyway, this is being recorded, so I think. Okay, what I was saying was that chi-square is about categorical variable. So it's about cross-tabulation. So when you cross-tabulate, you have one variable on one side, the other one one variable will be on the row, along the row, the other one will be along the column. Even when you are doing pair McNemas, The initial before will be along the row, we serve as if it's the exposure. The after will be the along the column, serve as if it's the outcome. But when you are doing goodness of fit, it's only one. You are not comparing two variables. You are not cross-tabulating per se. You have your data as one group, but you are just comparing with percentage they gave you in the population. So, and I said that even CASCA itself is a non-parametric test. So when Dr. Balogun go to that analyze and go to non-parametric. So how he went the other time, for goodness of it, go to analyze, go to non-parametric. Can you see? Normally all CASCA should have been under this, but because it's about cross-tabulation, that's why they put them under cross-tab, so that they go with all those odd ratio, any other thing that has to do with cross-tabulation. A kappa, if you want to do reliability kappa, if you look at under that cross-tab, anything that involves cross-tabulation is under it. That's why they remove it. But this one, they cannot put this one, the goodness of it, under that. That's why it's under non-parametric. And chi-square itself is non-parametric. It's actually everything supposed to be here. I think I've answered the question now. So if you now come to under dialogue, legacy dialogue, you will now see the chi-square there. Okay, Dr. Balogun, it's okay. You can stop sharing.
I've understood it.
Okay, that's great.
Understood. Thank you.
That's great. You can stop sharing, sir. You can stop sharing. Yes.
Understood.
I don't know what we have discussed. Goodness of it and McNema and Balka. I don't know if there's any question. Is there any question? So that we'll go and touch something, another thing before we close. Let's go to the concept of risk. Okay, if there's no question, it's well understood. Okay, no, it's not this one I want to. So let's so quickly look at measure of association.
It's completely off.
Nobody is talking. We want to quickly have a glimpse at what we'll be doing tomorrow. So we have finished with chi-square that tests association between either dependent group or independent group now, or goodness of it. But there's something about testing this association. You cannot quantify it. You just say, can you imagine? It's statistically significant, it's not statistically significant. So that's all it can do for you. But this association between sex and socioeconomic status, socioeconomic class, how do you quantify any association between two things variable? How do you know the weight? You can do your own study, you may say there's association. I do my own, there's association. The association may have weight more in one study than the other. Or association between this variable and another variable may have weight more than two variables like socioeconomic status, sex associated with it, level of education associated with it. Many other things may associate with it. Maybe urban and rural, where you live or whatever, or your profession may associate with it. But which one has stronger association? How do you know? Because when you do tell you, oh, the sex is female may are more likely to have higher belong to higher socioeconomic class. People with tertiary education or secondary education above are more likely to belong to upper class. Okay, which one is stronger? All these chi-square will not tell you, and that's why we're not talking about measures of association. So we'll be under the measure of association, we're talking like something like relative risk, odds ratio, and their confidence interval. So it's still all about categorical variables. But before we talk about this relative risk, odds ratio, let's understand what risk means and what odds mean. Risk is probability of an event happening. Risk is probability. Are we together? Probability is chance of an event happening. Is it? Risk is probability. It's only that risk is defined in different ways. You know, so there are some speculative risk in the sense that this event can be two-way. Just like somebody that you are investing, you either gain or lose. Or someone that go and play casino. You know that one is speculative risk. Because if you win, you get lump sum. If you lose lump sum also. So that's speculative risk. All those people that do investment, they know that the investment, they may lose their money. They may gain and gain more. They are just probability. Because if the risk sometimes can be two-way, can be one way. That's why the risk now have as if it's one specialty, but risk is actually probability. And risk doesn't actually have to be something bad. The people now, well, they look at it, okay, probability of an event you didn't expect to happen. Either it's an event you didn't expect, it's probability. Either it's the event you expect or you didn't expect. This is probability. And we have talked much about probability. Oh, well, not in this one, in some of, when we're discussing probability and normal distribution. But what I want us to look at now, the relationship between this risk and odds. We know risk is the probability of an event happening. What is odds? Odds is risk over 1 minus risk. You notice something, people that try to speculate, they want to bet for all these people that watch all those Man U, Arsenal, all those European league. They usually use odds to predict. You see the reason. There is a relationship between risk, though they calculate the odds from risk anyway, but they use it more than because it gives them more leverage than risk, which we're going to see later. Risk, all is risk over 1 minus risk. If I say the probability of it raining today is 0.6, the odds, what is the odds of it raining? It's going to be, that is 0.6 over 1 minus 0.6. It's like the probability of it not raining. So the probability of it raining is 0.6. The probability of it not raining is 0.4. It's 1 minus 0.6 with 0.4. So the odds of it raining is the probability of it raining over the probability of it not raining. Because the probability of it not raining is the probability is 1 minus probability of it raining. So that's why odds is risk divided by 1 minus risk. I don't know if there's any question. Does anybody want to ask a question concerning that? Okay, now, change your subject, if you remember, change your subject formula. If you play around this thing, the risk itself is odds over 1 plus odds. So if you get to, you can like mathematics, you can go and do change your subject formula. Use that first one. All is going to risk over 1 minus risk. Try to change to make risk the subject formula. You see, it's going to be risk, it's going to be odds over 1 plus odds. Now, if you calculate, probability is from 0 to 1. Probability cannot be less than 0, cannot be greater than 1. So the possible value of probability ranges from 0 to 1. Are we following Dr. Wakwe? The probability
I've been off for a very long time.
Is 0 to 1. Now, the odds is from 0 to infinity. If you want to get, okay, somebody, I want to give you assignment, 1 minute. If the probability of it raining today is 0.6, what is the odds? Calculate the odds. And give me figure. Let somebody give me figure. So I give you 1 minute to do that.
1 point. No.
What do you say? The computer has responded. Oh, yeah, what is the answer? Okay, let's give you 30 minutes, 30 seconds. Do it because I want to bring something up. I want us to calculate it.
Is it 1.5? I don't, but you
Yes,
said it should be
1.5, yes. Any other person, I was asking, any other person?
I got 1.5 initially,
It's
but
1.5
because you said
because it's 0.6 over 0.4.
The odds can be more than 1.5.
you
1.5.
said
Okay,
it can be more than.
Odds can be more than 1.
Yeah, thank you. That is what I want to bring out. So odds can be more than 1. In fact, it can infinity
1.5.
is from 0 to infinity. If you look at the table here, he calculates some probability and now calculate the corresponding odds. You cannot see the probability of 0.999. The odd is 999. The probability of 1, the odd is infinity. How do you know? The odd, probability is risk. Odd is if the risk is 1, which is probability, odd will be 1 all over 1 minus 1. 1 minus 1 will be 0. 1 all over 0, is it not infinity? It's infinity. Anything divided by 0 is infinity. So the odds ranges from 0 to infinity, while probability ranges from 0 to 1.
It is.
Now, that is the reason the people that speculate, they prefer to use odd, because when they are comparing two events, two things happening, if they calculate their probability, it will be maybe too close, or we calculate some events you want to speculate. If you calculate their probabilities, it will be difficult for you to make sure it's because of the closeness of the value. But when you calculate their odd, because the odd give room for, is from 0 to infinity, it will be obvious the one that is more probable will have higher odd. It will be able to detect the one that is more probable. That's why they use odd instead of using probability, using risk. Now, the measure of risk captures the probability that a particular event or outcome will happen over time. That's what risk talk about. Yeah, of course, the odds, you know what you mean, is the risk over the risk not happening. Can you see now? So you are trying to calculate how much more time that the event will happen compared with it will not happen. So in diagnostic test, when we do all this likelihood ratio in diagnostic test, when you calculate the cutoff with plot ROC, it's the same logic that is behind it. So when you look at odds, compare risk over absence of that risk. That is, you compare the probability of event happening over the probability of event not happening. If the probability of event happening is high, compared with it not happening, the odd will be high. So the relative risk, it compares risk for two events, two risks. Relative risk can also be called risk ratio because the way it compares to divide one risk by the other. So relative risk can be also be called risk ratio. Now, instead of me using, look at the table like this. You see a particular event. You will see reason they use calculating this risk, calculating all risk ratio or relative risk for event that is in future, because probability is about what will happen in the future. Now, you will see that in experimental design, cohort study, which they call longitudinal study, or the core and experimental, they are under the what they call longitudinal study, in the sense that you look for, well, because it's prospective, you look forward. So, for example, now, if some group are exposed to a disease and some people are not exposed, the risk of the disease between the two, you want to compare the risk of it. So, we want to compare the risk of the disease among the people that are exposed to the disease. Like, for example, somebody that is smoking is exposed to having lung cancer. The person that is not smoking is not exposed. So the risk, you want to calculate the risk of having lung cancer among the people that are smoking, that are exposed, compare it with the risk among the people that are not exposed. If smoking is going to cause lung cancer, we expect, if you now divide, because it's the numerator, the risk for that exposure, the risk among the people that are exposed is the numerator. Put it in the top. The one that are not exposed, the risk for them, if it is smaller, so the risk, when you divide the bigger by the smaller, it should give you something greater than 1. Now, I prefer illustrating rather than not just talking. This is what I'm saying. How many people are smoking here? 500 people are smoking, are smoker. How many people not smoking? 1,000 people that they got in the study. At the end of the day, when they follow up for some time, when you are still using this thing, even on Zoom, you are still using face mask on Zoom. So when you compare, you will see 25 people have lung cancer among the people that are smoking. 5 people have lung cancer among the 1,000 people that are not smoking. 25 people have lung cancer among the 500 people that are smoking. 5 people have lung cancer among the. So calculating the risk. How do you calculate? If you were to calculate the risk, what will you do? What is the risk of smoking? I want you to be interactive. So what is the risk of smoking amongst of lung cancer among the smokers now? Let somebody respond. What is the risk from here? I want you to be interactive. Nobody is answering. Because if it is physical class, what is, no, don't give me, just give, how will you calculate it? You may not even give the figure. What is the, how will you do it? It's all about division. So the risk is very simple now. The smoker, 25 people have 25 over 500. That is the risk. 25 over 500. That is the risk among the smokers. 25 over 500.
Yes.
The 5 over 1,000 is the risk among the non-smokers. And that is why they say the relative risk is the incident, the risk among the smokers. If you look at this table now, A, if you put A, B, C, D, when you add the A plus B, it give you AB, yeah? The total is just the same table we have been looking at before, by 2 tables. So that 25 was here. A was the 25 over A plus B, the 500. The C was the 5 for non-smoker over C plus D, which is the 1,000. So the relative risk, that is, you are dividing comparing 2 risks. The risk among the exposed, which is the incidence of disease, is A all over A plus B. The risk are not be non-exposed is C over C plus D. When you put them together, just leave that one. I want us to run it. When you run it, I will be able to explain. You see. Let's run the same thing. Who can share? There's a data file. Smoking lung cancer. Who has it? She will share with us, read it and share. Smoking, lung cancer, among the things I share with you. There's one that have smoking, lung cancer. There's lung cancer smoke, no, smoking lung cancer. That's the name. Who will share with us? Let me stop sharing so that the person can share. Or if there's any question, let me know. I want us to illustrate. Sometimes if you are just talking, I don't like talking too much mathematics unless there's something you can see to explain. That's great. So yes, click on the smoking lung cancer. That's the last one. The last file after the sec. Click on it, smoking lung cancer. Click on the smoking lung cancer. You have to double click on it. Who is sharing with us? Who is doing the sharing?
It's Balogun, Dr. Balogun.
Is Dr. Balogun, right?
Yes.
Yes.
Okay. It's not responding.
Can you see it?
But you have done. I want you to open it now in the SPSS. Double click on the something so that you can open in SPSS. If you double click, it will open the yes. That's great. Yes. Everybody can see.
Yes.
Yeah. So now go to, want us to see that table. Can you see the first column, long people that have lung cancer, people that smoke? But that's not, are you sure it's not? What's the title of that something you click on? It appears is the lung cancer smoke. Eh?
Yes. Yes.
It's not
Lung
it's,
cancer.
no, smoking lung cancer. That's right. It's not this one. Go back. It's smoking lung cancer. There are two files. There's smoking lung cancer. There's lung cancer smoked. It's smoking lung cancer.
Okay.
Yeah, yes, that's the one.
It's the next one.
Yeah, this last one. Yes, the one you are clicking. Smoking lung cancer. Yes, that's great.
Not this one.
Yes, that's it. Now, you will see there's a variable smoking, there's a variable lung cancer. Okay, we are not going. Go to analyze. You know, anything categorical where you're looking at the smoking is yes or no. Lung cancer is yes or no. So it's cross tab. Go to cross tab. So the exposure is smoking. Non-logistical, just smoking, yes. The outcome is lung cancer, the column. Now click on statistics. Click on risk. No, risk. There's a risk after kappa. Yes. Click continue. Click OK. Okay, okay. Yes. You can see the same table. The same table I was showing you in the slide. 25 people out of 500 people that are smoking. 25 develop lung cancer, 475 did not develop lung cancer. Out of 1,000 people that are not smoking, 5 develop lung cancer, 995 did not develop lung cancer. What it does is, what it just do is that they put 25 divided by 500, then everything divided by 5 divided by 1,000. So you calculate the risk among the smoking, which is 25 divided by 500. The risk among the non-smoker, 5 divided by 1,000. You now divide the first one by the last one. So the odd ratio is what you have as 10. No, and the relative risk is 10. If you do it with hand, you see that relative risk is 10. If you do it with hand, the relative risk is 10. That is, what he's telling you is that the people that smoke, they are 10 times more likely to have lung cancer. It's not just telling you, as if you put chi-square now, it will show statistically significant. That's all it will tell you. But this one is telling you more than that. Instead of saying it's statistically significant, more people that smoke, they are, no, it gives you that the people that smoke, they are 10 times more likely to have lung cancer and people that didn't smoke. Not only that, it now gives you 95% confidence interval. It ranges from 3.851 to 25.965. Now, I want to ask, which one is it significant? How will you know if it's significant or not? How will you know? Okay, let me share here because there's something. Let me share. Imagine you have, can you see me? Can you see I'm sharing something?
No.
So I share a whiteboard board. I share a whiteboard, you didn't see?
No.
I can see.
Okay, you cannot see the whiteboard I'm sharing, and I'm drawing something.
Yeah.
You are
I'm
drawing
drawing something.
something.
Can somebody
You can
see?
see it. You can see it.
If someone one person can see, everybody
Yes,
can
you can see it.
So let's say there's a scale of this 0, 1, 2, 3, 4, like that. So somebody just like that, increasing along this like that. If somebody have odd ratio of relative risk of 0.1 to 0.8, in between this place, somebody can have, that's 1. Somebody can have odd ratio between 0 point something to 3 point something. Somebody can have maybe after 2 point something to maybe about 7 or 6 point something. I want to ask question. This 95% confidence interval you are seeing. The odd ratio we just calculated, they say is 10. An example. But, okay, I didn't even put maybe up to 9, maybe up to 10, or to 12 self. And there is 10 here. Maybe this one have another person, okay, between this. Where is the brush? I want to ask, I gave 3 scenarios now. Which one is significant? The odd ratio that is 0.1 to 0.8, and the one that is between 0.1 to maybe 3 point something, and the one that is 3 point something to about 12. Which one is significant? Which one is not significant? It's good. Which one? Who can respond?
Narrow one.
Eh? What's the answer? Talk. Hello? No response. Okay.
The confidence interval.
If you don't unmute yourself, I cannot hear you. Nobody will hear you. You have to unmute yourself if you want to talk. Which one is significant out of these 3 scenarios? Which one is significant?
Eh? The one that has the lower, the narrower band.
Is the one that is significant.
The one that has lower band.
Okay.
Yes.
Okay, okay, thank you. Any other comment? Any other suggestion? Okay, let me just tell you straight. You know that I said, if you know the relative risk is about division, it's dividing the risk among a group that are exposed by the risk among the group that is not exposed. Now, if the risk is the same between both of them, that will be what the null hypothesis will say. Because one null hypothesis will say there's no difference. The risk is between the two groups. So if the same, maybe the risk is 10 and 10 here. 10 divided by 10 will give you 1. If the risk is the same between both of them, if your age is 45, another person's age is 45, you divide the two, it will give you 1. When two things are the same, you divide them, it will give you 1. It shows that there's no association, there's no difference in the risk. If there's no difference in the risk, there's no association. If there's no difference in the risk of lung cancer among the people that are smoking and people that are not smoking, there's no association between lung cancer and smoking then. So 1 means relative risk of 1 means no association. Now, if the relative risk is greater than 1, that is, if the risk is higher among the people that are smoking, it will, when you divide it, it will be greater than 1. It shows that more of the people that are smoking, they will develop lung cancer more than the people that are not smoking. If it's the other way around, that maybe less of the people that are smoking develop lung cancer, the numerator will be smaller than the denominator. That particular thing will be 0 point something. Now, whenever your odd ratio relative risk is 0 point something, it shows that the attribute, the one you put at the numerator is less likely to develop that attribute. It may mean that smoking, in this case, is protective if the relative risk is less than 1. But if the relative risk is more than 1, it can be 2, 3, 10, like this one. It shows that the people that smoke are more likely to develop lung cancer because when you divide it by the one that are not smoking, it's higher. It's more than 1 times. It can be 10, like in this case, like 10. 10 times more likely. If it is 2 times more likely. If it is 20, it's 20 times more likely to develop lung cancer. That is how to interpret it. Now, not only that one, when you now look at, that is what you get in your sample, but you are 95% confident that the range of value in the population will be between 3.8 to something, which we just see here. Now, to know if it's significant or not, whenever the confidence interval include 1 in the range, like this one and this one, it included 1, it steps from 0 point something and end empty after 1. It means that 1 is one of the value, and we already know that if it is 1, that shows that the risk is the same. There's no association. 1 relative risk of 1 means there's no association between the two variables. There's no association between lung cancer and smoking. So if you get something like you get a particular value, yes, then you now look at 95% confidence interval and the range, because it's telling you that in the population it can be any value between this and this. So if 1 is in the range, if it's 0 point something, and now then after, for you to get to 1 point something or 2 point something or 3 point, you have to cross 1 from 0. So if it has included that 1 in the range, that shows that it can be 1 then. Maybe if you do the study, another person do the study, they can even get relative risk of 1, because in the population, 1 is one of the possible value in the range that it can be. That's what it means. So when the relative risk, the confidence interval crosses 1, it is from 0 point something to anything after 1, it's not significant. But if it is crossing, if it is 0 point something to 0 point something, it didn't reach 1, it's significant. If it is anything after 1 to anything after that, it's significant also. Can you see? There are 2 scenarios that are significant here. The one that is 0 point something to 0 point something, and the one that is anything after 1 to something. Like in this our case now, it's 3 point something to something, which is significant. The only difference between the one that is 0 point something to 0 point something and the one that is 1, the one that is 0 point something to 0 point something means that the relative risk is less than is 0. Is less than 1, is 0 point something, and it means that that particular variable is protective. For if, let's say like that for this lung cancer, if people that smoke, they are less likely to develop lung cancer because the relative is less than 1. But if it is more, and the confidence interval also does not cross 1, it means that yes, the risk is higher among the smokers. You will see that there's it's the same concept, but slightly different. How you interpret relatively between when you are talking of relatively, how you interpret confidence interval when you are talking of relative risk and odds ratio. From when you are talking of difference between mean and proportion, the difference between mean and proportion, their own is 0. The confidence interval must not cross 0, because that one you are minusing. Here you are dividing. You know, when you are talking of a difference in that one, difference between mean and you are removing one mean from the other. You are removing one proportion from the other. If you remove one proportion from the other, if they are the same, it will give you 0. That's why their own, if the confidence interval crosses 0, it's not significant. But here you are not removing, you are dividing. In relative risk and odds ratio is division. The mathematical concept is division. You are dividing one that is exposed by the one that is not exposed. It is so whenever there is no association, if you are dividing the same thing of the same value, it will give you 1. If the numerator and denominator they are equal, it will give you 1 when you divide it. That is why it is when it crosses 1 for relative risk and odds ratio when you are interpreting confidence interval. I don't know if there's any question, because that's where the crux of the matter is. Any question concerning this? Any question? Is it that you are confused or you are? Because I'm even trying to see the people that are left. Because I can't see some people are logged out because of the internet. They are logged out. Dr. Balogun.
Yes, sir. I'm here.
So is it clear?
Yes, actually, it's very, very clear now.
That's great.
Yes, been working with zeros, crossing zeros, but now I'm hearing something.
Yes. You know, the other mean, when we talk about mean, proportion is 0. But when we are talking of relative risk,
1.
and it's crossing 1, and odds ratio is crossing 1. What of Dr. Wakwe? Dr. Wakwe, if you are responding, you didn't unmute yourself, I will not hear you. Dr. Isaac, is it clear?
It is clear.
That's great.
The confidence interval and this is clear.
Yeah, it's clear. Okay, that's great. So you will see something. We often say that the confidence interval gives more information. If you look at, okay, who run the, Dr. Balogun? You are the one that run the something now. Please go back, share it again. That thing you run. I want to share it again. Go back to that analyze. I want us to do something. Cross tab. Under statistics, go to statistics. Put also the leave. Just leave the risk. Also put chi-square up. Chi-square is up now. Continue. Okay. Also go to cell. You have run it. You leave it. You have run. Leave it. I wanted us to look at the percentage where you will see what I just want to say. You will see here that the chi-square is significant. When you calculate the chi-square, even continuity correction, yield corrected chi-square, likelihood ratio chi-square, which all of them are significant. It shows what I wanted you to go back. I wanted you to put that percentage so that it's not conventional way we interpret. Go and put that percentage. And go to cells. Click on rows. That's what I want. Rows. Row percentage. Yes. Continue. That's all. No column. Row. Continue. Okay. Click OK. Yes. Now, what I want us to see here is, it is obvious that, can you see, 5% of people that smoke develop lung cancer, as opposed to 0.5% of people that are not smoking. If you look at it, that's why it's 10 times. If you divide 5 by 0.5%, it's 10 times. So you can say that more of the people that are smoking, can you see 5% of the people that are smoking, they develop lung cancer. Only 0.5% of the people that are not smoking develop lung cancer. So it just gives you the association. But it did not measure it. That's P, you get your P value. That is the drawback of P value. But the confidence interval, we now go down. The one we did, go down now. You see, it show you the odds ratio. Okay, it's another. Okay, it's the one that just for the okay. Yes, the odds ratio table. Yes, the odds ratio they can tell you. Oh, the people. You are not. The computer is garbage in garbage. That's why it give you odds ratio, relative risk. The relative we are looking at here now. So it's you that know what you are looking for, because the computer will run similar thing, because it doesn't know what to put in, what you want to achieve. You run all the possible things you need. So the relative risk is 10. The people that are smoking are 10 times more likely to develop lung cancer. So you now give you 95. So it quantify it for you. It also give you 95% confidence interval to tell you that, to know the range of value within which you can find the real value in the population, because it's your sample from your study you get 10. It will not be actually 10 in the population. It's from your sample. You didn't study the whole population. You take sample, you go 10 times. But in the population, you are 95% confident that it will be between 3.8 times and 26 times. Between 4 times and 26 times. And you see it will range between. So the confidence interval give you quantify the association. It also give you the range of value, the interval within which you can find the population value. From the interval also you can detect if it's significant or not, which was what I was explaining the other time. So can you see, confidence interval gives more information, 3-fold information than p-value. That is why if you are publishing in Lancet, they will not even want to hear p-value. They want to hear what is the odds ratio and 95% confidence interval. What is the relative risk and 95% confidence interval? If you are dealing with mean and proportion, say what is the difference between mean and proportion and 95% confidence interval? That's what they want to hear. They say that it has no place in medicine. That is originated from industrial research in the early 19th, when they dichotomized research study into significant and non significant. They say it has no place in medicine. So I don't know if there's any question concerning that, because the way it's like people are becoming cold. It's like people are even logging out safe. Indeed, their internet is logging them out. So okay. So any question?
Well, okay, we are following.
Okay, that's great.
We are following, because the confidence interval, if one we are there or 0, then it means that there's a problem. We are following from what you told us.
And the 0 and 1 has to do with mean. It's not the ratio. It has to do with the means and difference between means and difference between proportion. That's 0. The 0 as the cutoff. But if it is ratio, like what we call ratio, relative risk and odds ratio, even hazard ratio, the confidence interval, if it crosses 1, it's not significant.
Yes.
Yes, I don't want to start new, because the way the atmosphere is. I want question so that we close. Tomorrow I will still do something because we are coming back. We look at the odds ratio also, not from confidence interval. We still talk much about this. Yeah, I want to get better way to tomorrow to illustrate it for you, because I know that some people got it. But sometimes some people, when they are no more flowing, they will not talk. By that time, they can decide to log out. They say they are in the network. So, any question?
Yes, I want, now we were able to see the risk function on SPSS. Do you have odds function on SPSS as well?
The risk function, yes, there.
What about the odds?
It is the same. You know, you go to know later when we talk about odd ratio tomorrow. Odd ratio is a proxy to risk. Just like the odd is a proxy to risk. If you look at it from the risk, you calculate odd. Yes, Amina. You know that you actually calculate odd ratio when it is impossible to calculate relative risk. So they just call it, they say they are all measure of risk. Yes, Amina. It's just like if you are not the HOD now, you can represent your HOD. Yes, Amina. But if your HOD maybe is not around your prof, you can say, oh, help me go and run my clinic. You are standing in for him. So it may be the relative review at the odd ratio. You are a proxy, you are standing in for him. But he cannot stand for you. You cannot say, oh, I will not be in the clinic, I'm traveling. Prof, run my clinic for me. You know, it doesn't make sense. You cannot stand. So the risk cannot represent odds. The odd can represent risk. That's why odd ratio is more universal than relative risk. It's commoner. Because that's why even in the logistic regression is the odd ratio you see. So that risk, the word risk, it does represent you. If you look at it, the table, it shows the odd ratio now. It's only that they don't know what we are calculating for this one. The next one, that other one that is lung cancer smoke. That one is the one that's talking of odd ratio. So we use the odd ratio for that one. So everything is there. Any other question? Dr. Wakwe, any question?